You know, we all have this picture in our heads of how the universe began, right? This massive explosion, this incredible expansion. But what if that story, the one that's been the blockbuster hit of cosmology for decades, is due for a major plot twist? What if the universe didn't inflate, but just popped into existence? And yeah, that's the big question we're diving into. Was the Big Bang really a bang at all, or was it more of a sudden snap? We're going to put the reigning champ, the theory of cosmic inflation, under the microscope. We'll look at the evidence that made it famous, but also the evidence that might be hinting at a totally different origin story. Okay, so here's our game plan. We'll start with the puzzles of the universe's first second. Then we'll dig into what the evidence really says. We'll introduce a new contender called emergence, put it head-to-head with inflation, and then talk about the hunt for gravitational waves, the potential tiebreaker. And finally, we'll see what this all means for the next chapter of cosmology. So to really get why this is such a big deal, we have to rewind the clock. I mean, way back, to the very, very first instant of the universe. See, when physicists started looking at the data from our cosmos, they ran into some super weird problems, puzzles that just seemed impossible to solve without some kind of special new idea. All right, so here's puzzle number one, and it's a big one, the horizon problem. When we look out at the oldest light in the universe, the cosmic microwave background, it is ridiculously, almost perfectly uniform. The temperature is the same everywhere. But here's the catch. Back in the day, the universe was expanding so incredibly fast that a spot on one side of the sky could never have been in contact with a spot on the other side. So how could they possibly have the exact same temperature? It just doesn't make sense. And then, cosmic inflation swooped in like a superhero with this beautifully simple three-step solution. First, it said, what if the entire observable universe was once smaller than an atom? At that tiny scale, everything could easily mix together and reach the same temperature. Easy. Step two, a mind-boggling, faster-than-light expansion stretched that tiny smooth patch to enormous cosmic sizes in an instant. And step three, that rapid stretching essentially froze that smoothness in place. And just like that, horizon problem solved. Pretty slick, right? So, case closed, right? Inflation seems like a total slam dunk. It's elegant, it solves this huge problem. But hold on. This is where the real detective work in science begins. We've got to be super careful and separate what we know for a fact, the raw data, from the story, the theory we've built to explain that data. And this is probably the most important slide to understand. On the left, you've got the core facts. These are the non-negotiables. Any theory, period, has to explain why the universe is smooth and why it has these tiny ripples with a certain pattern. But the stuff on the right, that's what we infer based on the inflation model, and especially a certain type of gravitational wave, what physicists call tensor modes. These aren't direct evidence for inflation itself, but for specific flavors of inflation, and that distinction is absolutely key. And that little crack in the door is where a challenger can sneak in. So let's try something. Let's forget about the how for a second and just write a job description for whatever happened at the beginning of the universe. What if some other process could do the same exact work, but without all the baggage of inflation, like needing a mysterious inflaton field or a smooth space-time that's already there to begin with? So what's on that job description? Well, whatever it is, it needs to do three things. 1, create connections across huge scales. 2, generate ripples from tiny quantum-level fluctuations. And 3, freeze those ripples into the structure we see today. And here's the big aha moment. Nothing on that list says it has to be done by stretching space. And that leads us right to this really wild, mind-bending idea. Think about it like water freezing into ice. It's a phase transition. The water doesn't stretch to become ice. It fundamentally changes its state. What if the universe did the same thing? It didn't start by stretching a pre-existing space. It started by becoming space and time, snapping into existence with all its properties already baked. All right, time for a showdown. Let's put inflation and this new emergent space-time idea in the ring together. How do they each handle those core facts we talked about? Let's see who's got the better explanation. Okay, first up, the horizon problem. Inflation's answer is like taking a tiny, smooth balloon and blowing it up to a massive size really fast. Everything was connected, and then it got stretched. Emergence has a totally different take. Imagine a huge network of computers that aren't talking to each other. Then you flip a switch, and instantly they all link up. That's the idea of a connectivity transition. A vast, uniform space is created all at once, not by stretching, but by connecting. Next round, explaining those ripples in the universe.
Inflation story is that tiny quantum jitters got stretched out to cosmic proportions. It works, but you have to get the conditions just right. Emergence, though, has what some physicists think is a more elegant answer. It points to something called a critical point, like water right as it's about to boil. At that exact point, you get patterns on all different scales, from tiny to large. That kind of scale-free behavior happens naturally at phase transitions.
Okay, so we have two theories, and both seem to do a pretty good job of explaining the basic facts. So, are we stuck? How do we pick a winner? Well, lucky for us, there might just be a smoking gun, a single crucial piece of evidence that could tip the scales one way or the other. And that smoking gun is something called primordial gravitational waves, or tensor modes if you want to get technical. These are literally ripples in the fabric of space-time, echoes from the universe's birth. The key thing is, many of the simplest, most popular versions of inflation predict that the violence stretching at the beginning should have created a whole background of these waves we should be able to detect. So this chart really sums up the whole battle. This first bar shows where most standard inflation models predict we'd find these gravitational waves. The second bar, for emergence theories, predicts a much, much weaker signal, maybe even nothing at all. And this third bar? That's how good our experiments are right now. We've looked, and we haven't found anything. This is a big deal. The fact that we're seeing nothing is already ruling out a bunch of the simplest inflation models. The pressure is on.
So where does all this leave us, honestly? We're at a really fascinating moment in the history of cosmology. The story we've been telling for 40 years, this elegant idea of inflation, is now facing a really serious and compelling challenge from a completely different direction.
All right, so let's boil this all down. What are the big takeaways? First and foremost, the data we have today does not scream it must be inflation. Not at all. Those core facts we talked about, they can be explained in other ways. And this idea of an emergent universe born from a sudden phase transition is a totally legit contender. And really, it all might come down to the hunt for those tensor modes. Which brings us right back to the beginning. Is our cosmic origin story one of a smooth, gradual stretch, or a sudden, sharp snap into existence? The amazing thing is, we don't know the answer yet. This isn't a history lesson. It's a live investigation. The evidence is still coming in, and the next discovery could change everything.